Welcome everyone. My name is Dominik Durner and today I'm presenting JSON tiles, fast analytics on semi-structured data. This is joint work together with Victor Leis and Thomas Neumann. In recent years, more and more data is created. And a large fraction of this data is semi-structured. Semi-structured data combine the schema information with the data itself. Therefore, they do not require a globally fixed upfront schema definition, as each individual document has all the information available to process it. JSON is the most common type of semi-structured data formats and stands for JavaScript Object Notation, which is further human readable. Together with the fact that JSON lacks any upfront schema definition, this often results in very poor performances for JSON analytics in database management systems. In this work, we present JSON tiles which solves this issue. In JSON tiles, we get the same performance as if the data would be stored as a relational table. On the right-hand side, you can see one example from the Twitter Tweet API. You can see different keys and values, but also quite some more interesting properties. For example, the user key contains a fully nested object within the outer document. Together with repetition, we can represent arbitrarily complex data objects. That's why JSON is widely used by web APIs and public datasets, because they can be read by humans, they're easily transferable, and you can represent arbitrarily complex data objects. But there are many more applications where JSON is useful. Another big application are logging of software systems. There, it's important that the human can directly grasp what happened to fix the issue. With JSON data, this is easily possible because you have all the meta information and the data itself combined together. Note that all of these applications are machine generated, and therefore the documents will have a very similar implicit structure. When we look, for example, at the tweets, you can see that all tweets will somehow have an ID, a user will create tweets, and they have a timestamp. There might be changes in the tweets, for example, the geolocation or the replies field, but overall the structure will look similar. The same holds for the logging of software systems. Different warnings will look quite different from the warning message. However, the structure will be looking quite similar. Analytics is very valuable for all of these use cases. However, it's also expensive. That's why even specialized tools were developed for parts of the application, for example, logging of software system. But those tools lack the flexibility and functionality of a general purpose database management system. So imagine you run a web shop and suddenly your web shop crashes. You might want to join your crash data with the order data to find out that a sudden spike in your orders resulted in the crash of the web shop. With that, I want to go into the processing of JSON within database management systems. But first, let me elaborate our three design goals. The first one is access performance. There we want to get similar performance as if the data would be stored as a relational table. Second, we want to have good query optimization capabilities and therefore need valuable statistics on the data. And lastly, we also need to be robust to changes in the data. Although most documents will look similar, we can have arbitrarily complex documents as JSON does not require any upfront schema definition, and the database management system needs to handle these as well. So let's dive into the previous approaches. The very first approach are binary representations, which is used in many real-world scenarios, for example in MongoDB or PostgreSQL. This already gives improved accesses because now the JSON string is in a more computer-friendly format and doesn't require any parsing anymore. However, you still need to go through the document to find the relevant parts, which doesn't give you the performance you're looking for. Further, the documents are still opaque to the database management system. Usually, the database management system does not have any insight into the contents of the documents, and this fact doesn't change when you transfer it in a binary representation. Another interesting field are raw parsers. There, you take the raw data and try to analyze it faster by using, for example, modern CPU features. You can already get better access performances. However, when you run queries multiple times on the same data, you always have to reprocess the data. At some point, it would be more beneficial to simply store it in a more computer-friendly format. Moreover, you don't get any additional statistics until you parse the data, so you cannot help the join ordering algorithm. Record trading is another very interesting approach which was developed by Dremel and is actually implemented in Apache Parquet. There, you take a JSON document and chop it into its individual pieces and store these pieces into column chunks. You already get statistics on the column chunks, so you have a min and max value, for example. However, when you recreate the documents, this can be quite expensive. Especially with nesting and repetition, this requires in Dremel the access of an automata. That's why another approach was developed called JSON. There, you take your JSON data and materialize the globally frequent parts of the JSON data into a new table. So you map the JSON data with a newly created table and automatically get the good performances you're looking for, and also statistics, as you can simply use the regular relational methods, for example, insert into. However, Sino cannot adapt, as changes in the document types cannot be reflected by this global approach. Further, outliers can create issues with Sino. That's why we created JSON tiles, where we automatically and transparently extract the frequent structures of only a local subset of the data. This local subset is then stored into column chunks, and with these column chunks we can create statistics and propagate them to table-wide statistics such that we can help the optimizer for join ordering. JSON tiles is able to handle changing document types by design, because if the JSON document changes, for example with the tweet API, geolocation was added later on, new tiles will see the changes and will directly adapt to them. Further, outliers and even the randomized insertions of heterogeneous documents can be handled by our reordering optimization. And lastly, if we do not have any materialized data for this key, because this is infrequent, we use an optimized binary format. With that, I want to go into our automatic extraction framework. We use again the Twitter Tweets API and show 8 tuples here. We mock the changes in the data by adding geolocation and replies later on. In this example, we use a tile size of 4, meaning that a tile needs 4 tuples to be created. The frequency for keys to be considered for materialization is 75%, meaning 3 out of 4. So let's dive into the first tile. There we can see that we can extract the ID, create the text, and also the nested user ID field with the right types. So when we join the data, for example with the user ID, we can directly use this integer. Note that tuple 4 also has the replies field. This is not frequent enough, and that's why it's not extracted in tile 1. It's a different story for tile 2. There we can extract all the previous columns, but also the replies field and the geolatitude. When we look at the geolatitude information, tuple 6 doesn't contain it, but it's still frequent enough to be extracted. With the Twitter example, JSON tiles already provides perfect extractable column chunks, as the insertion order is aligned with some spatial locality. For example, the geolocation is added on later on and is directly adapted by the newer tiles. However, there are datasets which have many different types and they only provide little spatial locality. For example, the Hacker News website. There, we also show 8 tuples here. We can see that many different entry types exist, for example story, polls, and comments. Although they share some common fields, ID, date, and type itself, all the other fields are actually type dependent. And even very fine-grained tile sizes wouldn't help here, as all of these documents are interleaved inserted. That's why we propose a reordering. In reordering, we take neighboring tiles and exchange tuples between them, such that one tile only contains one type of tuples, and then we can perfectly materialize this tile. We also have an example here. In this example, we use a partition size of 4, which means the tile 1 is neighboring to the tiles 2, 3, and 4. So each tile has 3 other neighboring tiles. The tiles have a tuple size of 5, and each individual tuple is identified with one tuple type, which is denoted by the colors here. So we have the green type, the yellow, the red, and the purple type. That a key is frequent, it needs to be occurring in 3 out of 5 of these tuples, so at least 60%. When we look at these partitions, we can see that each individual tile wouldn't be able to satisfy this frequency if there is no overlap between different types. And it doesn't matter if it's more structural, like in partition 1, or even uniformly distributed as in partition 2 and 3, JSON tiles would have a hard time to actually extract useful information. That's why we propose reordering. There, we group by the type and start filling one type into the first tile, usually the type with the most occurrences, which is the purple type in this example. So tile 1 is now fully materializable with purple typed tuples. We continue to do so with the green, yellow and the red tuples, and then we can see that only 3 outliers require the usage of our binary JSON format. Although tile 1, or partition 1 better to say, looks quite structured, we can see that the same holds true for also the randomized and uniformly distributed partition 2 and 3. There, almost all of the data is now extractable and only a few tuples require our optimized binary format. Note that this can be done in a parallel way as the partitions are actually independent of each other. But how are we actually identifying those tuples? We can use a frequent item set mining algorithm which mines item sets over the keys of the tuples. Therefore, we find identifiers for the tuples to be reordered according to our previous slide. We can also reorder within a tile to, for example, use run length encoding, because when we have one type in one region of the tile, we can get both better compression and faster accesses as the rest of the tile will be null values. JSON tiles uses an adapted FP growth algorithm, as in comparison to a priori, FP growth does not need to generate candidate sets. However, the result complexity of an item set mining algorithm will still be combinatorial in the number of items. That's why we start to compute smaller item sets first until we reach a budget, because otherwise we would stall the database. This helps to find good identifiers and on the same time have a running database management system. Lastly, if we do not have any materialized data for infrequent keys, we use our optimized binary format. And this format provides accesses in objects in logarithmic types, time in the number of keys. Further, arrays can be accessed in constant time. We also require that we do not have any memory address jumps, because we want to optimally utilize the caches. Therefore, we build the nested objects within the outer object, such that we can go continuously over the data. With that, I want to go into the experimental evaluation. We use Umbra for JSON tiles, which is the database management system developed here at the Technical University of Munich, which supports SQL in columnar storage. We compile our queries to LLVM code. All the experiments we show later are run on an AMD Threadripper with 64 GB DRAM, 16 cores and 32 hyperthreads, and the data is initially stored on a Samsung SSD. We have different competitors. First of all, the internal ones, which are implemented within Umbra. We have JSON, which is the human readable format. We have the binary JSON format without any materialization. We use the Sino approach and our relational tiles version. We further have real-world competitors, for example PostgreSQL with its JSON-B format. We also use Spark with Parquet to show the Dremel approach, Spark with MongoDB to get the BSON of MongoDB combined with the joint capabilities of Spark, and we use HyperAPI, which is a scalable system that can use JSON documents. So let's start with the scan performance, and there we use the TPCH query 1. But first, let me explain how we can get a JSONized TPCH version. So we take the column names and combine the column names with each individual row of a table. So we take the column names, make them keys in documents, and then each individual row is the values for these column names. So we get one document per row. We then combine that into one JSON column and then run our JSONized TPCH queries. Query 1 shows that our JSON tiles approach can outperform the competitors by a large margin. When we look into the internal competitors, we can see that JSON tiles provides performance improvements of 7x compared to the binary JSON baseline. We can also see that with a rising number of threads, JSON tiles scales almost linearly. We also look onto different queries, for example query 18, which is more heavy on join and aggregation performances. There we can see, although we spend less time for scanning the data, we can outperform the competitors by a large margin which is partly due to our better join ordering. In the internal competitors, we can see that JSON tiles also scales quite well there until we hit hyperthreading. Hyperthreading is not useful for query 18 anymore because it's too computation heavy. I already mentioned tile sizes and partition sizes, but I didn't yet quantify good values for those. In these experiments with the TPCH and Twitter datasets, we show the tile sizes on the x-axis and the different colors of the graphs denote the different partition sizes. Note that we plot the geometric mean of the queries, so less is better. We can see that with an increasing number of partitions, we get better performances. However, the improvements get less and less the more partitions we add. When we look at the loading times, which directly are in conflict with more partitions as we need to reorder between more tiles, we can see that with a medium-sized partition size and a small number of tiles, we do not have any overhead with reordering. That's why we propose to use 2 to the power of 10 for tile sizes and a partition size of 8, because then we can combine the best of both worlds. With that, I want to conclude that JSON tiles achieves all the 3 design goals we mentioned earlier. It almost has relational access performances. We allow the query optimizer to find better join orderings, which help, for example, in query 18, and we're robust to heterogeneous data by using our reordering optimization. Thanks for your attention.